This is your presenter, Asloob Mudassar, and I am presenting slide number 18I of the course on atomic and molecular physics. In the today's lecture, I shall be covering the following topics: interaction between rotation and vibration, the Dunham expansion, rotational barrier. This is the ninth lecture of the series on molecular physics. And this is in continuation of the previous 8 lectures. You must go through previous lectures, that is from lecture number 18A to 18H, if you want to really understand this lecture. Interaction between rotation and vibration. A real molecule simultaneously rotate and vibrate. The vibrational frequency is higher than the rotational frequency by 1 to 2 orders of magnitude, which is explained in the figure. The nuclear distance changes periodically during one full rotation. For example, you can see in this figure, there is a dotted black circular path. This circular path is actually the distance RE, that is the equilibrium separation between the two nuclei. And this distance is fixed, because the RE distance is fixed. So this dotted curve, this dotted path, this dotted black path shows that the distance is fixed. And there is another path which is shown in the blue color. And the two atoms, for example, over here and over here, are connected through a variable distance between the two nuclei represented by R as a function of time. And you know that this is going to, and capital S is the center of mass, and the rotation arrow indicates that this is rotating. And two different orientations are shown. For example, along this curve, along this straight line, two atoms or two nuclei are connected, and along this horizontal line, another path, another instant of time indicates the rotation at this point. So you see that when this will rotate, that is these two nuclei connected with a line with a line represented by R of t. When this will rotate, the separation between two nuclei represented by R as a function of time, this will change with time. Sometimes it will increase, sometimes it will decrease, and this will be a periodic variation between the value. That is, sometimes the value of R of t will increase beyond the value of Re, and sometimes it will decrease. And this periodic variation in the path of in the separation between the two nuclei is important, and this will happen when the molecule will rotate. And the separation between the two nuclei represented by R of t will be a function of time and will follow a periodic path as it is indicated in this figure also by the blue path. So as J is equal to I omega is equal to constant, and you know that J is the rotational quantum number represented by I omega is equal to constant in time. So if this quantity is constant in time for a freely rotating molecule, so for a freely rotating molecule, J is equal to I omega is equal to constant, but I changes periodically. Because here capital R will change, that is the separation between the two nuclei will change periodically as a function of time. So I will change periodically. So omega has to change with a period t vibration. So you see that since this quantity J is equal to I omega is equal to constant, and I, as I said, that I will change periodically, it means that in order to keep J constant, omega should also change periodically with a period t vibration. The rotational energy will also change with t vibration, which is given by E rotational is equal to J into J plus 1 h bar square over 2 mr square. Because you see that mr square is actually the quantity I, moment of inertia. So it means that the moment of inertia, if it changes periodically, it means mr square changes periodically. So E rotational will also change periodically. And usually this diagram actually explains the vibration of the rotor. When the rotor vibrate, then you see that the distance between the two nuclei, which is represented by capital R as a function of time, will change with the time periodically. That is, sometimes it will exceed by the value of RA, and sometimes it will decrease as compared with the value of RE. So that is why it is called a vibrating rotor. As the total energy has to be constant, there is a periodic exchange of rotational, vibrational, and potential energy in the vibrating rotor. So you see that as the molecule rotate, the total energy of the molecule has to be constant, which is given by equation number 170. So E on the left hand side is the total energy of the molecule, and on the right hand side it is composed of the rotational energy E rot plus VIB, which is the vibrational energy of the molecule, and E pot, which is equal to the potential energy of the molecule. So the sum of these three quantities is equal to constant. So when, for example, E rot changes periodically, then of course the other quantities will also change in such a way that the total energy E on the left hand side remains constant. This energy flows classically between the potential and kinetic energy of the vibration and rotation, and is illustrated in the figure. So you see that the exchange between the potential and the kinetic energy will take place of the vibration and rotation. Now let's look at this figure and first go through the caption. Mean internuclear distance R averaged, average value of R, and the rotational constant BV, which is the vibrational constant, is proportional to the average value of 1 over R square. And these two quantities have been shown for the harmonic potential, shown on the left hand side as A, and unharmonic potential shown in part number B, that is on the right hand side of this figure. So you see that both of these figures show the potential. On the left hand side we have the potential, which is the harmonic potential, and the minimum distance and the minimum separation is at RE, which is the equilibrium separation. And you see that I have shown some vibrational level. This is the minimum energy of the vibrational level represented by 0. Then this is the first vibrational level, second vibrational level, third vibrational level, and then the fourth vibrational level. So you see that the average value of R has been represented by the hollow circle. So you see that I have shown hollow circles at each vibrational level, which indicates the value of the average value of the molecule during its rotation. And you know that when the molecule will rotate, it will rotate in this parabolic path at its extreme values. That is, you see that this horizontal vibrating curve cuts the parabolic at two extreme points. So it means that the molecule vibrate between these 2 points of the parabola where the horizontal line interacts. And then of course you know that obviously the average value during this rotation will be equal to at the center. Now let's look at the other curve, which represents the unharmonic potential. And you know that this is not a symmetric potential. That's why it is called the unharmonic potential. And it deviates on the right hand side as compared with the harmonic potential. Again, you see that I have shown the equilibrium separation between the nuclei represented by Re, and I have shown in this unharmonic potential horizontal lines representing the zeroth vibrational level, then the first vibrational level, second vibrational level, third vibrational level, fourth vibrational level, and so on. And you will notice in this diagram that the vibrational levels more or less remains constant, seems to remain constant for the first maybe 3 or 4 levels, but you see that after that one it is noticeably changing, that is the separation between the vibrational levels will change. That is, there will be a decrease between the vibrational energies and between the vibrational levels from level to level. For example, it is quite obvious that the levels between vibrational quantum number 5 and vibrational quantum number 6 is significantly smaller in comparison with the vibrational separation between the vibration level 0 and 1. Moreover, when the molecule is at any vibrational level, for example, in the vibrational state 3, with the quantum number V is equal to 3, the molecule will vibrate between the extreme positions of this unharmonic oscillator, where the horizontal line intersects with these 2 points of the unharmonic oscillator. So this is the position where the molecule will oscillate between the two extreme positions of this unharmonic oscillator. But you know that the average value has been indicated by the solid circle. As you see that it's obvious that the average value of R is represented by the solid circuit in this solid circle in this unharmonic oscillator. And you know that this is not in the center as indicated by a black arrow perpendicular to the R axis. So it is deviating because it is the center of this unharmonic oscillator. Each point represents a average value which is deviating from the center as compared with the harmonic oscillator. So in the unharmonic oscillator, the average values from the unharmonic oscillator for the vibrational levels will change from level to level, as it is obvious in this diagram. Now you see that in the middle I have shown for the paths of these the separation between the averaged values of the vibrational levels represented by the curve A and also by the curve B. In the curve A, I have the hollow circles, and in the curve B and in the straight line B, I am showing the solid circles. So the line B represents actually the mean averaged path in the unharmonic oscillator, whereas the hollow circles in A represents the average value or the mean values of the molecular oscillations in the harmonic oscillator. Now you see that I have shown these two, but you know that the curve A in this curve A is actually slightly bending. That is the straight line A is slightly bending in comparison with the line B. But you see that, for example, the lowest vibrational energy in the two systems is the same. That is the zeroth vibrational level in the harmonic oscillator and the zeroth vibrational level in the unharmonic oscillator. They are at the same position. So I have shown these two in the middle of this diagram. Both are at the same position. But if you go in the higher vibrational levels, you will see that the separation between the vibrational levels, that is the separation between the solid circles, will change more will change slightly less as comparison with the hollow circles in the line A, because it is also obvious that the separation between the unharmonic oscillators will decrease with the vibrational as we go along with the increase in vibrational levels. So for a few levels, it may seem to have the same values, because I have shown for V is equal to 4. For the quantum number V, vibrational quantum number V of V is equal to 4, they may seem slightly the same. But if you go beyond this one, there will be a significant change between the separation between the vibrational levels in the unharmonic oscillator as compared with the harmonic oscillators. And you know that I have also depicted the value of Re squared multiplied by the average value of 1 over R square is equal to the ratio of the BV to the BE. And you know that these are the two constants which I have already defined in one of the previous lectures. So let me read the caption once more. Mean internuclear distance capital R averaged, the average of the capital R, and the rotational constant B proportional to 1 over R square, the average of 1 over R square. These two quantities are shown for the harmonic and the unharmonic oscillators shown on the left of the figure and the right of the figure. The rotational energy obtained from the time independent Schrodinger equation is the time average over a vibrational period. So you see that if you solve the Schrodinger equation and obtain the rotational energy curve, you will get this rotational energy as the time averaged as the time average as the time averaged energy over a vibrational period, because since we have averaged quantities, that is we have the averaged value of r in these vibrational levels. So it means that we, since in the rotational level the average value of r is involved there in the formula, since r has to be changed through its averaged value, therefore the rotational energy is also given for the averaged for the time averaged for the time averaged formula, and the average is written over the capital R, and over one for one period for one vibrational period. This time average can be calculated as presented. So now you see that I am now going to give you the formula for the average value of a capital R and also for the average value of a 1 over capital R, so that you can understand that what are the values of average value of R and what is the average value of 1 over R, so that you can understand that how the rotational energy will change for the harmonic oscillator and for the unharmonic oscillator, because the average value of a capital R for these two oscillators will change with vibrational levels. The probability to find the nuclei within the interval dr around the distance r is given by, this is the P of r is the probability of finding the electron or finding the nuclei at a distance r multiplied by dr, that is we are considering an interval dr around the point r, and this is given by the absolute square of the vibrational wave function as a function of r multiplied by dr. Now you see that if you wanted to calculate the expectation value of a capital R and the expectation value of 1 of capital R, these are given by the following formulas shown in equation number 172 and 173. So the expectation value of R is equal to the integral of psi star multiplied by R and then psi and then the dr, and the subscript with the psi indicates that is the wave function corresponding to the vibration levels. And similarly you can calculate the expectation value of 1 over r square represented by the averaged value and given by the formula on the right hand side, which is the integral of psi star of vibration wave function multiplied by 1 over r square multiplied by the vibrational wave function and then multiplied integrated over the interval dr. So the expectation value of a capital R or the classical counterpart is the average value of a capital R. Similar, the expectation value of 1 over r square or the average value of 1 over r square is are given in equation number 172 and 173. When we use the average value, it means that we are talking about the classical values, and when we talk about the expectation values, it means that we are talking about the quantum mechanical quantities. The mean rotational energy averaged over one vibrational period is given by. You see that in the rotational formula, we have the value of capital R. So let me show you this formula over here. So you see that you have 1 over r square. So you have r square appearing in the denominator of the formula of E rotational. So when you want to calculate the average value of the rotational, you need to take the average value of 1 over r square, which can be provided by the expectation value of 1 over r square given by the formula shown in equation number 173. So the mean rotational energy averaged over one vibrational period is given by averaged value of rotational kinetic energy as a function of the vibrational quantum number is equal to j into j plus 1 multiplied by h bar square divided by 2m, and 1 over r square has been represented by the value of expectation value of 1 over r square from equation number 173, which is written over here. So equation number 174 gives you the average value of the rotational kinetic energy of the molecule during its rotation, and the average has been performed over one vibrational level. Even for harmonic potential, the average value of R is equal to Re, which is the equilibrium separation, is independent of the vibrational quantum number or the vibrational state. For example, here you can see from this formula, from this diagram on the left hand side, that is for the harmonic oscillator, the value of average value of R is the same as Re. So the average value of R will not change from the level, from the vibrational level to the vibrational level. So even for the harmonic oscillator, the average value of R, which is equal to Re, is independent of the vibrational quantum number, whereas the value of 1 over R square, average value of 1 over R square, or the expectation value of 1 over R square increases with V. And this is also obvious from this diagram on the right hand side, that as you go along the value of R, you will find different average values of R, and of course 1 over R square, and these will change with the principal quantum, with the vibrational quantum number V. So BV also depends on V. For more, this can also be seen from the previous diagram on the right. For more realistic unharmonic potential, both expectation values decrease with increase in quantum number, vibrational quantum number V. The rotational term values can be expressed in BV instead of BE. So BV, you know that I have given a formula of a BV in one of the previous lectures. And from that formula, I am going to find out the value of a BV. So BV is equal to h bar over 4 pi cm, and the integral of psi star of the vibrational wave function, which is a function of two variables V and R, multiplied by 1 over R square, and then again multiplied by the vibrational wave function, which is also a function of V and R, and then multiplied by dr. So this is an expression of a BV in terms of the expectation value of 1 over R square. BV is averaged over the vibrational motion, because you see that all the quantities where we have used the expectation value of 1 over R square, it means that those quantities have been averaged over complete one vibrational level as the rotational energy, as the average value of the rotational energy of the molecule, and also the constant BV. BV is averaged over the vibrational motion. It depends on the quantum number V, vibrational quantum number V. For a Morse potential, you see that Morse potential is a very important potential, and unfortunately I am giving you the mathematical form of this Morse potential for the first time in this lecture. I should have talked about the Morse potential much earlier, but nevertheless, it is never too late to. It is never too late. So BV is equal to BE minus alpha E times V plus half, where V is the vibrational quantum number. This alpha E is much less than BE. An average centrifugal force constant is defined by, so average centrifugal constant, you know that I have also defined this constant earlier, and now I am giving the value, average value of this constant during the average rotational motion of the molecule. So this dV is equal to h bar cube divided by 4 pi c k m square, and the integral of again psi star multiplied by 1 over r6 y vibrational multiplied by dr, because the original formula of dV contained 1 over r6, And since we are talking about the average value, so I have multiplied the constant term by the integral, which is giving the average value of 1 over r6 for the expectation value of 1 over r6. Because before that, when the molecule was not rotating, the value of dv and the value of dv were constant. But now these two constants will change, as I have explained them in 176 and in equation number 177. And it can also be related to the value of dE, which was also defined earlier, but now I am defining this dV again. So dV can be given by dE. dV is equal to dE plus beta E times V plus half. And in this equation, again, beta E is much less than dE. For general potential, higher order constants have to be introduced. So you see that as I have defined these constants, for example, I have defined the constant BV in equation number 176. I have defined constant DV. I have defined constant DV in equation number 177, and also related to the constant DE in equation number 178. I can expand BV and DV using equation number 176 and 178. And this is the expansion of these terms. And you see that the first is BV is equal to BE minus alpha E times V plus half plus gamma E times the square of V plus half, and so on. Similarly, dV is equal to dE plus beta E times the value of V plus half. Similarly, that delta E times the value delta E times the square of V plus half, and so on. So I have shown up to the squared terms. So you see that for the simplest case, we can retain the terms up to the first power. For more accuracy, we can retain up to the terms for the second order, and for even more accurate results, we can include the third powers also. The term value of a rotational vibrational level can then be expressed as the power series. So on the left hand side, I have the term value, which is a function of the vibrational quantum number and the rotational quantum number V and J respectively. And on the right hand side, I have dE, which stands the kinetic energy of the electrons, plus this square bracket, which is containing, you see that different terms with the different powers. And this term value has also been given in my one of the previous lectures, and from that lecture I am reproducing the value of dV for the rotation for the molecule which is rotating, and I am incorporating different values over here. And you see that in the square bracket there is another square bracket containing the value of BV into J plus 1, which is the rotational contribution to the term value. BV multiplied by J into J plus 1 minus DV multiplied by J square into J plus 1 squared, and then multiplied by HV multiplied by J cube into the cube of J plus 1, and so on. And you know that I have already given you the value of BV, dV, and HV. I have not mentioned the value, but similarly we can write the value of HV as I have written the value of BV and dV. And I have also written their expansions in the previous lecture, in the previous equations, for example, in these two equations. Similarly, you can also write an expression for the value of HV, because I have also given a formula for HV in one of the previous lectures, and you can modify those formula for the HV, and similarly you can write an expansion for the value of HV for the constant HV also. And you know that the first square bracket, which is a larger square bracket, is due to the contribution from the vibrational levels or the vibration of the molecules. And I have here the molecule is vibrating with a vibrational quantum number V, and I have expressed these terms in one of the previous lectures, and I have borrowed this term from one of the previous lectures. So this is the main square bracket is actually the contribution due to the vibration of the molecules, and the small square bracket which contains the vibrational which contains the rotational quantum number j is actually the contribution of the rotation of the molecules to the term value of the molecule. For a Morse potential, this series reduces to. So you see that I have explained you, I have given a formula for the Morse potential. So now if you want to write the term value for the Morse potential, you will write the term value in the way as given in equation number 182, and equation number 182 has been derived from equation number 181 when we are using the Morse potential instead of the unharmonic potential. So T for the Morse potential as a function of the two quantum numbers of vibrational quantum number V and the rotational quantum number G is equal to TE plus omega E times V plus half minus omega E into XE times the square of V plus half plus VB into J plus J into J plus 1 minus DV into J square and into square of J plus 1. So you can notice very clearly that using the Morse potential, the equation which is given in equation number 181 has been simplified to a great extent in equation number 182. And the results obtained from the Morse potential are very satisfactory and much closer to the experimental data, and also a simplified version in its simplified version. Now I am going to define the Dunham expansion. The term values T of V and J of a rotating molecule for a more general potential is given over here. And this more general potential which I am mentioning is given in equation number 18.167. And from that one, I have written the potential given below, but in a slightly modified form. That is E potential as a function of R is equal to summation over N, AN multiplied by the nth value of the nth value of R minus RE, where AN is equal to 1 over N factorial multiplied by the nth partial derivative of E potential with respect to R and evaluated at a value of R is equal to RE. So this is the same potential written in the slightly different form using equation number 167. So Dunham introduced the expansion, that is T, that is the term value of the rotating molecule as a function of the quantum numbers V and J is equal to two summations. One is a summation over I, the other is a summation over K multiplied and contains y of Ik as some constants, which we call Dunham constants, Dunham coefficients multiplied by V plus half raised to power I, and then j into j plus 1 minus lambda minus capital lambda square, and this whole bracket is raised to the power k. So this equation 183 is actually the contribution of the Dunham, which is also known as the Dunham expansion. The Dunham coefficient Yik are chosen to make the term values T of Vj to satisfy the experimental data of the measured term values of the rotational levels in a vibrational state of the molecule. That is, when the molecule is rotating as well as vibrating, the Dunham term value T of V and J gives a formula as given in equation number 183, which satisfies greatly the experimental data. The coefficients that describe the vibrational rotational levels of a molecule are related to the constants as given. Now you see that we are going to correlate the Dunham coefficients with the coefficients which we already know. For example, Y10, Y10 is approximately equal to WE, omega E. Y20 is approximately equal to omega E times XE. Y30 approximately equal to omega E times YE. Similarly, other constants are related. The other Dunham coefficients, that is the Y coefficients, are related with the other coefficients that we have already discussed in the previous lectures. Now let's talk about the rotational barrier. The effective potential of a rotating molecule. Now we are talking about effective potential. The effective potential of a rotating molecule includes potential, this potential, that is E potential as a function of R, and with a superscript V mean that this corresponds to the vibrational level in state V. So the effective potential of a rotating molecule includes the vibrational potential, this E part as a function of R of a non-rotating molecule. So this potential which I have written E potential as a function of R at vibrational level of vibration level V corresponds to a non-rotating molecule, and a centrifugal term is given. So you see that we are representing now the effective potential in terms of two quantities. One is the potential for the non-rotating molecule and other is the centrifugal term as given below. That is V potential, V effective potential as a function of R, which is for the rotating molecule, is equal to the E potential as at corresponding to the vibration level V as a function of R. This is the for the non-rotating molecule plus the centrifugal term, which is J into J plus 1 multiplied by H bar square divided by 2 mR square. For a bound electronic state, this potential, that is the effective potential, is minimized at a distance Rm, where Rm is the distance, where Rm is the minimum distance, that is the distance at which this effective potential is minimized, obtained by equating the first derivative of equation number 184 with respect to R and setting that derivative equal to 0. And then you solving that equation for the value of R is equal to Rm, you will get this equation given in equation number 185. So this will give you the minimum value at which the effective potential is minimized. So Rm is the value of R is equal to Rm is the value at which the effective potential is minimized. So if you use R in equation number 184 by the value of Rm, then this will give you the effective potential minimized. So Rm is given by J plus 1 multiplied by H bar square divided by capital M, and the derivative of E potential with respect to R. This whole term is raised to the power 1 over 3. The derivative term gives the slope of the rotation less potential. That is, when the molecule is not rotating, then the potential, then this will give you the potential of then this will give you the slope of that potential, which corresponds when the molecule is not rotating. The minimum value of E effective potential is shifted by the rotation of the molecule from value Re to the larger distances, and the dissociation energy becomes smaller. As you see that this is shown in this diagram. Let me read the caption first. Effective potential curves. So you see that I am using the word effective potential curves of the rotating sodium molecule, sodium diatomic molecule, for different rotational quantum number J. Since you see that E effective potential, which I just mentioned as given in equation number 184, depends upon the value of a quantum number J in explicit sense. So using different value of J, you can plot this function, and you will notice that the minimum of this effective potential is shifted to the right, that is towards the longer value of Re, that is to the longer value as compared with the value of Re. So you see that, for example, for J is equal to 0, the Re value is over here. But as you plot this potential, that is the effective potential for higher values of J, for example, J is equal to 120, this is slightly shifted to the right. So with J is equal to 150, it is even more slightly shifted. And for J is equal to 200, even more slightly shifted. So for J is equal to 250 and for J is equal to 275, the minima of these potential curves are shifted on the right hand side of the minimum of the value of RE, which is the equilibrium separation. So you see that if you go for higher value of rotational quantum number J, you will notice that the minima of these curve will shift to the right, that is will shift to greater value of R. And when it is shifted to the greater value of R, then of course the dissociation energy is also minimized. So the energy level E, which is the function of vibrational quantum number and a rotational quantum number above the dissociation energy ED, can still be stable if they are below the maximum of the centrifugal potential barrier. So this is shown in the next diagram. For example, this diagram. This Vj represents a vibrational level in this potential. So this is one of the potential from the previous diagram. And you know that this potential crosses this vibrational level, which is also shown and extended by the dotted curve, by the dotted straight line, horizontal line. And this represents a vibrational level corresponding to the quantum number J, any value of J. And this is a vibrational level in this potential curve. And this potential curve is represented by the En of R. And this Ed is the dissociation energy, that if you provide this much dissociation energy to the molecule, which is sitting at its equilibrium value over here, then this molecule is dissociated by providing this much energy. And you know that if this level, that is the vibrational level, if even this level lies above the dissociation level, the molecule could even be in a stable state, provided that this level Vg is lower than the maximum value of this curve. And you know that the maximum value of this curve is lying over here in this region. This is the maximum value of the potential. And if the vibrational level, which is lying above the value of the dissociation energy, this level can even exist for a stable molecule if this level lies below the below the if this level lies below the dissociation, if this level lies below the, if this level lies above, you know that this level, which is the vibrational level corresponding to the quantum number J, is lying below the maximum value of the potential, but lies beyond the value of the dissociation energy. Even then, this level, which is the vibrational level, can also, a molecule can also exist in this level in a stable state. And when the molecule penetrates through the rotational barrier, then the molecule will be de-excited and it will emit, the fragments will emit kinetic energy. And this will, the difference between the dissociation energy and the energy of this level will appear as the kinetic energy of the nuclei A plus B. So you see that here the point is that the molecule with its potential, with its vibrational level lying even above the dissociation energy, can still be in a stable state, the molecule will still be in a stable state provided this vibrational level is lying the highest value of the potential, which you can see that here the value of the potential is the highest, and this level is lying slightly below that, but this level is beyond the value of the dissociation energy. So this value, if this level has to be dissociate or have to be undergo dissociation, then this level has to pass through the rotational barrier. And the caption of this figure is a pre-dissociation of a molecule through the rotational barrier. That is, the molecule has to pass through the rotational barrier if this level has to be dissociated. The energy level E, which I have shown you as a function of the quantum number V and J, which lies above the dissociation energy ED, can still be stable if they are below the maximum value of the centrifugal potential barrier. Centrifugal potential barrier. And you know that here is the centrifugal potential barrier. This part of the barrier that lies above the value of dissociation energy is called the centrifugal potential barrier. This is. So if our level is lying below the centrifugal potential barrier, this is the centrifugal potential barrier. So if this level is lying below the centrifugal potential barrier, then of course the molecule with the vibrational level V would even be in a stable state whether the level is existing beyond the value of the dissociation energy of the molecule. But you know that if the molecule is in this state, it has to overcome this centrifugal potential in order the molecules to be disintegrated. And during this process, the molecule during the disintegration process will emit the kinetic energy, which is constituted by the nuclei A and B. Molecules in these levels can dissociate by tunneling through the barrier, known as the dissociation by tunneling through barrier. So you see that I have shown you the level. I have also shown you the centrifugal barrier. So there should be a tunneling, and the dissociation will be through the tunneling process known as the dissociation by tunneling through the barrier, which is also known as the rotational barrier. The tunneling probability depends exponentially on the width of the barrier and on the energy gap between the maximum of the barrier and the energy level. So you see that the tunneling probability will depend upon the width of this barrier, which is this. This is the width of the barrier from this point to this point. So it depends upon the width of the barrier as well as the height of the barrier. So the tunneling probability depends exponentially on the width of the barrier and on the energy gap between the maximum of the barrier and the energy level, which is shown in the diagram. So you see that this diagram shows different copies of the centrifugal potential. So there are many copies of the centrifugal potential depending upon the value of J, starting from J is equal to 0, then J 120, 150, 200, 250 and 275. And you see that this is again the barrier potential or the rotational potential or the rotational barrier. So this is the centrifugal barrier or the rotational potential. And you know that I have explained this rotational potential in this diagram. And you know that in this potential I have shown two levels, two vibrational levels for each of these potential. For example, for the potential labeled with J is equal to 150, I have shown the vibrational level which has a value of V is equal to 25, and for this level the value of J is equal to 150. And you know that again this level is lying above in such a way that this level is below the value of the centrifugal potential, but you know that it is beyond the value of the centrifugal beyond the value of the dissociation energy. Similarly, I have shown another level for the green curve. For the value of J is equal to 200, the level is the vibrational level is shown, which has a value of V is equal to 10, V is equal to 10, and J is equal to 200. And again, for this level, I have shown the centrifugal potential over here. Above the dotted line, there is a centrifugal potential. And you know that I have explained these pre-dissociation potential or the centrifugal potential or the rotational barriers with this diagram in much greater detail. The pre-dissociation rate can be determined by the width delta E, which is equal to h over tau. So you see that here I am talking about the width delta E, which is equal to h over tau of the levels with a lifetime tau, where tau is the lifetime of that corresponding level. If the pre-dissociation rate is large compared to the radiative lifetime of the level, and you know that the pre-dissociation rate is defined by this equation, that is delta E is equal to h over tau. So if the pre-dissociation rate is larger compared to the radiative decay of a level, the lifetime tau is mainly determined by the pre-dissociation. That is mainly determined by the value of the centrifugal potential or the rotational barrier. Tau as a function of a variable as a function of vibrational quantum number V for all the levels above the dissociation limit gives information on the form and the height of the potential barrier. So you see that the information about the potential barrier can be obtained from the value of T as a function of vibrational quantum number V for different levels. The dissociating fragments above A, the dissociation fragments have a kinetic energy shared according to their masses. That is the kinetic energy is shared by the masses of the two nuclei, that is the nucleus A and the nucleus B. So these two fragments will share the kinetic energy to the system, and it depends upon the masses of the nuclei A and B, and is given by the formula E kinetic is equal to the energy of the level, which is E as a function of V and J minus ED, which is obtained at J is equal to 0. That is J is equal to 0. You have the value of ED. This is the value of ED. From this to the top value of red curve, this is the value of ED. And you know the values of these levels is given by E as a function of V and J, because these vibrational levels are the function of V and J. So the kinetic energy shown over here will be obtained by the difference between these two values. That is E kinetic energy is equal to E of V and J minus the dissociation energy for the curve corresponding to J is equal to 0. So you see that in this lecture, I have explained interaction between the rotation and vibration. for harmonic anharmonic potentials, for the Morse potentials, average value of rotational kinetic energy, average value of different constants, then expansion of these constants, then the term value in terms of this value, then the Morse potential was used to simplify the equation number 181 to equation number 182. Then the Dunham expansion was given, and the expansion formula for the term value is shown in equation number 183, and the Dunham coefficients were given over here. The rotational barrier for the effective potential was explained. Through these curves and also through this curve. So this is the end of slide number 18I. The lecture is still continued on molecular physics.